Okay, good morning everyone. So today is lecture 13. We'll continue talking about Xfoil. In the last class I talked about how at least my recommendation for how you can install Xfoil and how you can set up the folders. So I'll mention some things here and then I'll go to the computer to demo it in Xfoil itself. So one of the things you need to do is you need to know how to load an airfoil. Right, so many NACA airfoils, or some at least, can be generated in Xfoil itself. So those are not a problem, but then often you have to load an airfoil from some other database, somewhere on the web, or sometimes later on you'll be using Profoil to design your airfoils and you have to load that in. So we'll talk about how to do that. So you can read it from a coordinate list in a file. And the default sign convention for this is usually this will be x equals 0, sorry, x equals 1, and this is x equals 0 usually, right? It doesn't have to be like this, but usually that's how it is. So the coordinate lists will be x, y coordinates starting from here, and then you go around, you give one list of x, y coordinates and then come back here. So the file will look like this. The first line can be an airfoil name, and this is optional, this line is optional. So if your first line is not an airfoil name, that's okay. And then you have coordinates like this. So you start with the trailing edge on the top surface, like this point is the trailing edge, but you go along the upper surface. And then go along like this and come to the leading edge, and as we'll see shortly, this you don't have to have a 0, 0, okay, but for at least this page I'm going to say here's the leading edge, and then you go back to the trailing edge. So let's look at this in some more detail. So you have one, this is the trailing edge, and then you have 0, 0, right? That point is optional. So this leading edge coordinate often the data sets will not have that. So you might have points that go like this, and let's say this is the leading edge, right? You might have a point just before and just after and your coordinate list will not have an exact 0, 0, and that's fine. Xfoil knows that it'll create a spline through existing points, and even if there is no 0, 0, that's fine. So and another important point is do not repeat the leading edge coordinate point. And that's actually true for anywhere along the airfoil. You should never have two successive coordinates be the same. Except maybe the trailing edge, right? The trailing edge, you start off with the trailing edge and then you go back and you can have the same coordinate, but don't do that for the leading edge. And the reason this can happen is if you go to some database coordinates, if you download some coordinates from the database, right? Sometimes they will give you coordinates for the upper surface and lower surface going from 0 to 1. So this is leading edge and this is trailing edge. And then they'll do the same thing for the lower surface. And this is leading edge and this is trailing edge. So in such cases, what you have to do is you have to actually flip this coordinate list so that this goes through, you're flipping it so that it will come in this format. So it will start from the trailing edge upper surface, go to the leading edge, and then go back to the trailing edge. But when you do that, when you flip this, you'll have a 0, 0 here, and then you'll have another 0, 0 here. And that's where you have to remember to remove one of those 0, 0s. You shouldn't have consecutive points that are the same coordinate. And the reason is Xfoil will interpret that as a break in the splining, and it will create a sharp corner there, and that causes trouble. Okay, let's now switch to the computer. Okay, I hope you'll be able to, are you able to see this from there? So I'm in the, because I don't, this is a classroom computer and I don't have admin privileges. I am working in the downloads folder in a folder called Xfoil. Right, so let's just start Xfoil. And when you start Xfoil, you see something like this. Right, it starts off with Xfoil version 6.99, something or the other. And it says xfoil.def not found. We'll talk about this later. I mean, that's fine. Most of the time, that's okay. And then you see all these menu items. So these are all commands that you can use. So it comes with a prompt here. And so at this prompt, you can put in any of these commands. And you can also see that some of these commands have a dot before them. That means that command will open a sub-menu, or it'll go into another page sort of thing. So maybe the best thing to do now is to say NACA. There is an option here saying NACA and then I. That means you can type NACA like 0012 and it will create a 0012 airfoil, or you can type a 5-digit 23015, something like that. So there are a couple of ways to do this. You can say NACA, enter, and then it will say enter 4-digit or 5-digit. Let's say just say 2412. Right, now it will create the NACA airfoil, and it's done the paneling. And it's telling you how it has created, what kind of paneling it has created. So number of panel nodes is 160, panel bunching parameters, and then there are some various other details of how the paneling has been done. So there is a command here called ppar, which has got a dot there. That means it's going to open up a submenu, and this means show or change paneling. So let's go to that. So when you do this, it opens up this graphic, and it also here, it opens up, it tells you these are the paneling parameters, and then it says change what, and CR just basically means return, it's carriage return. Anybody know why it comes? What is carriage return? Yeah, it comes from back in the typewriter days when you do ching, that thing I think is called a carriage return. I don't know. Basically it means enter. So if you want to change any of these things, if you want to change n, number of panels or panel bunching parameter, or most of the time I don't touch this except the panel nodes. Number of panel nodes is something I usually set at 200. So I'd like you all to use 200, because then I can compare results with what I'm generating and see whether you're doing things or not correctly or not. Because of course the answer is going to depend a little bit on the number of panel nodes. So in our class we'll all use 200. So you can say n, and you can say 200 right away there. And then if you're done with it, I think now the graphic will also be updated. No, the graphic is not updated. It still says 160. But if I go and say I'm done with it, right? I don't want to change anything else. So hit enter. Then I think now the graphic will be updated. So the graphic has been updated, and this is 200 panels on the airfoil. Okay, so this is, and then you can zoom and unzoom. So if you want to zoom into the leading edge, for example, if you type Z and enter, it says mark off corners of blow up area, 2 identical points default to current area, right? So like here you can go and say I want to zoom into this area, and it tells you it zooms into that area. And I think these lines are the unit normal vectors or something like that. These are normal vectors at those points. And if you come back here, you can say unzoom, and now you're back to the original zoom setting. Okay, and then you can hit enter, and you're back to the main menu, right? At any time, if you want to know what are the menu items, like right now, we don't know what the menu items are, right? If you put question mark and hit enter, it'll tell you these are the menu items. These are basically the choices you have. Okay, so that is how you use an NACA airfoil, or that's how you generate an NACA airfoil. One thing you do is, I'm not going to be able to go through all the menu items, so you should actually spend some time reading these things. Just look at this and see what all possibilities are there. There are some that we won't use because we are not going to use Xfoil for design in this course. We'll use Profoil for design. So there are some like QDES. QDES is a surface speed design routine. This allows you to change the velocity distribution on the airfoil. There is MDES, which is complex mapping design routine. So those are things we won't use. OPER is something we'll use right now. We're going to do that. Likewise, GDES sometimes you'll use. GDIS is a geometry design routine. You can use it to set a trailing edge flap. And then you can use save, psave, isave and msave are really not relevant to what we are doing. I don't know, I think psave probably writes it to a plain coordinate file without a header line, whereas save probably puts a header line. And then load is something we'll use a lot, NACA. I mean, there are other options which may be useful in future in some other circumstance. So PPAR is what we did just now to change paneling. And plop is plotting options. That might turn out to be useful at some point. And you can specify airfoil name if you want. You can create a version number and do all those kinds of things. So now what we have in our Xfoil is the 2412 airfoil, right? So let's save this to a coordinate file just to see how it looks. So save. I'm going to call it n2412.dat. I mean, I have the practice of naming my airfoil coordinate files with a .dat. That's just my practice. You can do what you want. Sometimes I've called it .xy just to remind myself when I look at the coordinate, when I look at all the files in a folder, if it's .dat or .xy, I know that's a coordinate file. I'm not going to confuse it as something else. So let's do this, and then I think it's probably already written. Yeah, there's a file here called n2412.dat, and I don't know. Yeah, let's open it with, I prefer using WordPad. Okay, there's WordPad. Actually, I don't use any of these editors. I use Emacs, and I don't think Emacs will be in this computer. In my desktop and laptop, I have Emacs. So anyway, now you see how the coordinate file looks. This is what Xfoil has created. So the top header line is just the name of the airfoil, and then you have coordinates going from the trailing edge, and this is all upper surface. And there should probably be 201 points because there are 200 panels. And then somewhere here is the leading edge. For some reason, it didn't put the leading edge exactly at 0, 0. And this would happen on and off, and it's just the way airfoil geometries are. They won't be perfectly at 0, 0 sometimes. But you can see this is all upper surface, and then you start going to the lower surface now. And then it'll come back to 1, and so this airfoil has a slight bluntness in the trailing edge, which is why it's got a slight negative Y value at the trailing edge. And likewise, if you go to the top, there's a slight positive Y value at the trailing edge on the upper surface. So it's got a slight bluntness. So when you have a blunt trailing edge airfoil, which means it doesn't come to a point, then you don't close that. So you just start from the top trailing edge, go around to the bottom trailing edge, and you leave it as an open gap, and Xfoil understands that to be a closed trailing edge, right? If you try to close it, then it's not meant to be closed, is what I'm saying. Internally, Xfoil will take care of that. Any questions? So now let's run this airfoil. Let's do an inviscid analysis. So basically, when you want to run an analysis, you have to use this opper. And for some reason, they've called it direct operating points. Basically, direct operating points means you're saying, go run it at this alpha, go run it at this lift coefficient, something like that. So if you type opper, it goes into a sub menu, right? So now you have opper, and then there's an I. I means it's in inviscid mode. If you go to viscous mode, this will change to V. So that means even while you're looking at it, if it says upper I, it reminds you that you're in inviscid mode. And if you want to know what to do next, you always hit a question mark, and there are all these options. So you can change Reynolds number, Mach number, you can change a lot of these different things. You can toggle between inviscid and viscous mode, which we will do soon. You can prescribe the alpha, the inviscid CL, the actual CL, or sequence of alphas, sequence of lift coefficients, and do all those things. Let's start with the simplest, and then you have various plotting options. Okay, so let's start with the simplest thing. Let's type an angle of attack. So to analyze this at an angle of attack, remember this is an inviscid mode. So if you say alpha, ALFA, it will say enter angle of attack, and let's say 0 degrees. And it's actually, that's it, it's done the calculation. And if you go to the other window, where is that? Here is the graphic showing the CP distribution along the chord for the upper and lower surfaces, and that's the geometry of the airfoil. On the right, you have the name of the airfoil, angle of attack, lift coefficient, moment coefficient, and this is CD pressure. And really CD pressure should have been 0, but this is a numerical method, right? So there is going to be a small amount of CD. I'm kind of surprised it's this high. But anyway, even in inviscid flow, it will end up calculating a CDP because it is a discretized airfoil and a discretized pressure distribution. And just like in homework 1, you saw that even in inviscid flow, you would get a small amount of CD, and that's what this is. So you can see this is upper surface pressure coefficient plot, and this is the lower surface. And this axis, like we normally have been plotting, the bottom of this axis is +1, then it goes to 0, then it goes negative. Okay, so this is if you want to do one angle of attack. You can go and say, I want a bunch of angles of attack, and that will be a sequence, ASEQ. Right? You can give the number straight away, or you hit enter and it will say enter the first value, let's put 0, enter the last value, let's put 12, and alpha increment is 2. And now it will give you these CP distributions for alphas listed here from 0 to 12 in steps of 2. So this is 0, 2, 4, 6, 8, 10, 12 on the upper surface, and these are the lower surface corresponding plots. So obviously 0 is the inside one, and then the 12 is the outside one. And the corresponding CL values and the pitching moment coefficients are shown here. So this is all pretty straightforward. Any questions?
It's pitching over that the chord was giving you?
Correct. So there is by default, the pitching moment is about x equals 0.25, y equals 0. And I think there's a way to change it somewhere here.
In the main menu, I think there was a way to change what CM references.
Okay. So let's go and see where that is.
Is there any reason why you need to change the y value from 0?
The y value from 0, like,
0.25 and 0. I was wondering if there's any reason why you want to find the pitching moment.
oh, if somebody has done experiments and they're reporting it at some point other than 0.25, 0, then if you want to match their experiments, you could go and set that same value here. There may be some reason maybe somebody is trying to make an airfoil that's free floating about some hinge, and that's not at 0.25, and then you would probably go and do. There are all these situations that will come up that sometimes you don't know why it's there. There are usually options here that you will say, why is that there? 2 years later you'll come to a situation where that will come in useful. And a lot of this has been, I think, done that way. So when a new situation arises and some need is there, probably Professor Drela went and coded that up and created a new item. Okay, so let's go to the main menu. And yeah, so here is XYCM RR, right? That RR means you can type in that number straight away there, or you can hit enter and it will say what is the new X reference. I don't know. What happens if I say, I just hit enter. Now I think if you hit enter, it'll not change anything. Usually that's how it is. Yeah, so change CM, currently 0.250. That's where is the reference. Okay, any other questions? There is also some menu items, like in the main menu there is a thing called norm. Let's go and see that. That means the loaded airfoil will be normalized, and what this is useful for is, let's say you're putting coordinates in from an actual model. So you have a wind tunnel model or something and you take it to some digitizing machine and they use a digitizer to digitize all the coordinates and you put that into Xfoil. That airfoil may not be exactly horizontal, right? It might be at some angle and the length might be some weird units. So norm will usually tilt it, I think it will rotate it and scale it down uniformly so that the leading edge goes at 0, 0, trailing edge goes at 1, 0. So the chord becomes 1 and the longest length becomes parallel to the x-axis. That's what norm does, I believe. I mean, some point you might, if you use it, you should probably just test it, give some examples and make sure that's what it's doing. Yes, one more thing. Let me look at that and then I'll come to a question. So let's look at PLOP. Somewhere here there is a way to, yeah, so if you want color postscript output, this might be useful later on. You can toggle this. So if you say C here, the postscript output will be true. So how many are wondering what postscript is? I mean, I think very few programs nowadays write postscript files. Postscript is something like a predecessor of PDF. Adobe used to have postscript files, then they went to PDF, but these programs were all written before that, right? If you have Adobe Acrobat, you might need the professional version. It'll convert a PostScript file to a PDF file, or you can download something called Ghost View. It's available for Windows, it's a free program, and that will open PostScript files, and then you can do screen capture from there and copy that and put it in Word, for example, and do things like that. So this is where, in the beginning of the course, I gave a document with a couple of pages of something like useful instructions and general suggestions and tips, something like that. So this is where sometimes, if you create a color PostScript output, sometimes some of those colors will be in yellow or green or something. And let's say you create that, you go and do a screen capture, and you open it with Ghost View or something, go to screen capture, put it in Word. Yellows almost don't show up against a white background. So even though there is a color postscript output option available, sometimes it's just best to stick with black and white, because later on we'll see this when we do polar files. You'll have lots of lines comparing different airfoils. Let's say you're comparing 3 airfoils and you're plotting the drag polar. You'll have 3 lines, and if one of those is yellow, it'll just almost be invisible. But if you keep black and white, Xfoil automatically gives different line types, and it's actually pretty clear. So just because there is color, don't go and use it. Sometimes it's just not worth it. So I made color postscript output as true. I can do C again, and it'll toggle it back to F. Like that, you can have landscape, font size, and all that sort of stuff. Okay, so hit enter and back to Xfoil. Let's go to Opper. So we talked about how to do inviscid analysis. There's not a whole lot to it. That's all there is. Inviscid analysis, you put the alpha and it'll give you the CP distributions. You can write all these things to a file, and we'll see that shortly. You can also run an analysis for a given lift coefficient. So let's say CL of 0.5. I want to see how things look at CL of 0.5, and so immediately it went and figured out the angle of attack needed to get you CL of 0.5, and it's done this. So this is okay for inviscid analysis, but I wouldn't recommend putting a CL in viscous analysis. I'd rather you put angle of attack and figure out the angle of attack that will give you a certain CL. I mean, in some situations it's okay, but usually in viscous analysis, putting a CL can result in some problems, and we'll talk about why shortly. Okay, so let's go and look at the viscous analysis. Let's look at the menu items. So there are a whole bunch of menu items, but basically the first menu item is Visc, and this toggles between inviscid and viscous mode, right? So let's type Visc, and pretty much the first thing it will want to know is what is the Reynolds number, right? Viscous analysis cannot be done without knowing Reynolds number. We'll run this at 3 million, and so you can put the Reynolds number here as 3, 1, 2, 3, 4, 5, 6. That's 3 million, but if I remove a 0, it still looks more or less the same. It's so easy to make a mistake, right? I put 3 and 5 zeros, and if you do this without noticing, you'll run this analysis for 0.3 million, thinking it's 3 million, and it'll all come out wrong. So I'm telling you these things because over time I've made mistakes and then realized, that was a silly mistake. But these are like human factors things, right? You won't notice it. So you can do 3E6, and this is a better sort of foolproof way to enter the Reynolds numbers. This way you're very clear what you think you're putting is what you're actually putting. So now it'll tell you, okay, you've entered the Reynolds number, 3 million. So it says, okay, now Mach number 0, Reynolds number is 3 million. That's what it's going to run the airfoil at. Let's type, when you do viscous analysis, you should start at some good angle of attack, something that's, could you shut the door please? You should start at a condition in which the solution is likely to converge. So remember we talked about viscous analysis is the part where it'll do an inviscid calculation with the panel method, then it'll do a boundary layer, then it'll correct the geometry, it'll take the effective geometry and do an inviscid analysis on the effective geometry again. So it's essentially, it loops between the panel method and the boundary layer calculation. So it's an iterative process. Iterative processes always have conditions in which they won't converge. And that will happen when you're trying to do beyond stall, or in some situations where there's a big laminar separation bubble. Those are hard conditions, right? Hard, difficult situations. So the numerical methods won't converge. So in many of those situations, you have to start with good initial conditions. You have to give a good guess, and then it will converge. So we'll talk about why that's important, but maybe let's start by saying that you start at a good angle of attack, usually 0, 2 degrees, depending. If you have a flap angle, sometimes 0 is not a good angle, but usually 0 is fine. So I'll just type A0. So the other thing is there are also shortcuts available. So instead of typing alpha, you can type A. As long as, well, yeah, I think that's what this means. You see that sometimes you have menu items that are in all caps, PWRT. Sometimes it's just A capital and then LFA. That means, I believe that means if you just type A, Xfoil knows that it's alpha. Or if you type C, that's enough, it'll know it's CL. Or if you type AS, it'll know it's A sequence. And these are useful when you're running things interactively, like running on the screen, seeing what the results look like. But also many times you won't do this interactively. You will put all these commands in a file, which we'll call a script file. It's kind of like a macro. And then you will just send it to Xfoil, and Xfoil will just do all these things and give you it'll write the files and create all the graphics and store everything. But when you're running interactively, you want to do this really fast. So A0 means angle of attack 0. And it did 7 iterations of the inviscid and viscous calculation, and then it converged. I know it converged because if it didn't converge, it will say here not converged. So let's go scroll up. So it does all these calculations: wake trajectory, source influence matrix, solving boundary layer, system initializing boundary layer, and then some blah 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 something. And remember, all the time it's calculating transition, it's calculating the boundary layer, and as the boundary layer, after every iteration, the pressure distribution changes, so it will do the loop using Newton iteration, and every time the transition is also changing. So it's calculating a whole bunch of things, and you can see how fast it went. So, even though you might think that this is written in some ancient language, it's not really ancient. Fortran is still, I would say it's pretty much the go-to language if you want speed, and you can see how fast things went. Okay, so it converged after 7 iterations, and it's telling you angle of attack is 0, CL is 0.2422, pitching moment is this, CD is this is friction drag, this is pressure drag, or friction CD, pressure CD. And if you look at the graphic, that's what it shows. So CP distribution, these are the results. It tells you, so if you actually take this graphic, it has a lot of good information. For example, it's put the Reynolds number here. Reynolds number is 3 million. So let's say you sort of print this out or something, or copy this and put it in Word or something, and look at it 4 months later. This graph has got all the information to remind you pretty much most of the things that you like to know. And this is sort of, it's worthwhile thinking about it in our own work as engineers. Frequently, you'll make plots and you'll have 2 or 3 lines and you'll say, well, I kind of know what is what. I'm not even going to put a legend, or I'm not going to say what it is. I'm not going to put a title. And then and most of the time you guys are doing it for homeworks and stuff, right? But when you're doing it for research, you're going to come back to things like this 6 months later, and you look at this and you won't even remember what you did. So it's just good practice. Think about, these are sort of lessons we should all learn as we use different software or different tools. And this is something I find very interesting. So one of the things with Xfoil homeworks in our courses, you'll have plots like this. You can also write these things to data files. So some people will actually write these things to data files and they'll plot it with MATLAB, which in theory is okay, but it won't have all this information. So when I ask you to make a plot with Xfoil, I'd rather have the actual plots from Xfoil than some post-processed version that you create yourself. Because in your post-processed version, I'll not be able to say what the Reynolds number is. You will probably give the answer for some Reynolds number, but I won't know for sure if you ran it correctly. Whereas if you give me a plot like this has the information I'm looking for. Not just this, later on in polar plots, we're going to talk about some polar plots. There, you will see all the nice information that this Xfoil and the associated software, they generate it in a form that's really the way airfoil designers need. Okay, coming back to this. So it's color coded, the upper surface is in yellow, and like that, even the velocity upper surface is in yellow. There are actually two lines here, right? One, the dashed line is the inviscid result, and the solid line is the viscous result. So it kind of shows you how much viscosity has changed the pressure distribution. The light blue line is the lower surface, and then it calculates the CP distribution in the wake also, and it shows you kind of how the boundary layer thickness looks. And then it gives you all these results: angle of attack, lift coefficient, moment, drag, L over D, and N critical is a parameter that you can change to mimic more free stream turbulence or less free stream turbulence. Default of N critical of 9 works well, but there are some situations, like for example, our wind tunnel is not a low turbulence wind tunnel. So when you test airfoils in our wind tunnel, usually they compare with Xfoil better when you use N crit of 4, because the wind tunnel has got more turbulence than an aircraft flying in the atmosphere, where the free stream turbulence is much smaller. Okay, so that's how you run an angle of attack. Now, I mentioned that you can also run a lift coefficient, right? So now the problem when you run a lift coefficient is, for small angles of attack, it'll probably work well, but so it's doing an iteration between viscous and inviscid, right? It's doing panel method, boundary layer, and it's looping that. When you ask it to do a particular CL, on top of that, it'll also iterate on alpha. And so sometimes things will get, especially if you're trying to make it do a lift coefficient near stall, it's just varying a lot of things and the numerical method won't converge properly. So it's better to just run alphas in viscous mode. So now if you want to run a sequence of angles of attack, you can do that. You can do a sequence. And what it'll do here is, so let's say I do first alpha. I've already run angle of attack 0. So if I say first alpha of 0, it's going to use the converged boundary layer from the previous calculation and use that as the initial starting point, and it'll go to the next alpha. So because I've already converged 0, it'll converge the first alpha, which is 0. And then I'm going to give the last alpha as, let's give 15 degrees, and I'll do step size of 0.5. So it'll go every half a degree from 0 to 15. And this is what I was talking about. Numerical methods converge better when you give good initial conditions, right? So at every angle of attack, it will use the previous converged solution as the initial condition, and then it will do that. So So first it will do 0, then it will do 0.5, right? When it goes to 0.5, it will use the boundary layer solution from 0 as the initial guess. And so if you give small changes in alpha, you're going to be very close. And so your initial guess is going to be really close, it will converge nicely. So even though you're doing a bunch, now we are doing some 30 angles of attack, right? But each one will converge very quickly. Whereas if you do 0 in steps of 5 degrees, between 0 and 5 there's a big change. And between 5 and 10, 10 and 15 you're going through stall. So there's a big change. So when it uses the previous angle of attack as the initial solution, the guess is not really good, right? So it'll have to do a lot of calculations to try to converge, and it may not converge. So it's a good idea to give small alpha increments. In fact, sometimes we give 0.25 or 0.1 when you're going on the negative angle of attack side. Sometimes it's good to give even smaller ones. Okay, so I'm going to run this 0 to 15 in steps of 0.5, and you can see it just flies through, and you get these CP distributions, and these are all converged viscous solutions. So it converged all the way to 15. And you can see some of these CP distributions are like this. That's because the flow is separated. So it's given alpha, and it went down below the page actually. CL, CM, CD, transition location, upper and lower. And you don't have to worry about copying these numbers or something. You can always write them to file. We didn't do it, but I'll show you how you can write them to file. So this is the CP distribution. And because we ran from 0, we converged at 0, and then we did small step size, it actually went all the way to 15 degrees and it converged there. And this may not always happen. So let's try to come up with a case where X-foil will not be successful. Sometimes it's hard. Let's try 0 now. I don't know if it will work or not. Probably will work. So remember, when I type alpha 0, the previous thing it's run is 15 degrees. So it will try to use the converged boundary layer from 15, and then it will go and do a 0 with that as the initial solution. So you're making it a very difficult problem. So I don't know, we'll see. Yeah, it failed to converge. So the same 0 that ran earlier now does not run, because you're making it come from a very far away initial condition. But by default it runs 10 iterations. There's a way to change that. But basically it said, well, I've tried 10 iterations, it's not converged. You can, when you're running in interactive mode, if you wanted to keep trying more, you can say exclamation point and hit enter, and it'll do 10 more, and you can keep doing this. Basically, after 35 iterations, it actually converged. So that's one more thing. So by default, it will run 10 iterations, and you can change that, I believe, somewhere, iter. Yeah, this iter will change the number of iterations. So you can give it 100 or something if you want. Usually, if it doesn't converge in 100 iterations, it's not going to converge. And it'll stop, right? It'll try 100 times, and it'll just give up and go on.
Is there a way to reset it just automatically? If you ran 0 to 15 and then you want to run 0 again, so you get 0 back. So how do you erase these?
Correct. That's an important question. I'll come to that. So, but the other thing is, if it doesn't converge, so most of the time we'll write all these things to data files, right? We won't be looking at screen stuff all the time. So if it doesn't converge, it won't write that data to file, which is a good thing. So when you go and look at the file, all of those are actually converged results. Otherwise it wouldn't have written it. Okay, so we can type iter, and it'll say current limit is 10. I'll make it 25. Now to the other good question. So the latest alpha we have run is 0, right? This is actually very similar to the earlier one. It actually converged properly. But now let's try to write to alpha of 20 degrees, which again is a difficult problem. We have run 0 and we are suddenly making it jump to 20. It'll probably do 25 iterations and it's not converged. And if you want to see the graphic, it'll look like this. Yeah, so this is the inviscid CP distribution. You can see this huge suction peak, and it's just having a very hard time doing it. Let's keep making it go. Converged finally. And this is actually how the solution looks. This is a pretty separated flow. It's beyond stall, I would assume. And you can see this is the boundary layer. Right, this is the upper surface boundary layer. You can see it's separated somewhere here and it's become a massive separation. And the pressure distribution has this big suction peak, and then it becomes more or less flat. CP will become almost horizontal when there's separated flow. And you can see that CD is pretty high, lift coefficient is this, and so on. So this kind of plot it will do only when you do a single alpha. When you do a sequence, you're already doing a bunch of angles of attack, so it won't plot boundary layer and stuff. So this is nice for visualization and things like that. Okay, so now, any questions on this? Yes?
On the previous plot, it looked like where the transition occurs, that there's what looks to me like a small laminar separation bubble, or I don't know if that's what it is, or just transition.
Yeah. Okay. So to answer that, and while we are on this plot, we can go and plot some things about the boundary layer and things like that. So let's go to question mark, and one of the menu items is P. Where is that? CP. You can do, there's something called CPV, right? Let's see what that is. It's a little fun plot. This plots the pressure distribution, and you can see this massive suction here. And this is a pressure distribution plot. I mean, this is just like he says, it's GWiz. It's not terribly useful. Boundary layer variable plots. This is sometimes useful, and it's actually useful even for your homework. You'll need it. VPLO, and it's a submenu. It's a submenu within a submenu. So there are two dots, and you do question mark to see what's there, and it tells you can plot all these things: kinematic shape factor, delta star, edge velocity. So let's type UE. So this is the UE over V infinity plot. It's the kind of stuff you had in your data files. Upper surface, lower surface, and again look at all this useful information it writes. And this is the reason why it's being used all over the world. It's just such a well thought out program. Okay, so the stagnation point is here. This is the upper surface, this is the lower surface. Now another plot that's often useful is CF, skin friction coefficient. So here's the skin friction coefficient, and you can toggle the lower limit of this, I believe, by saying y-axis limits on the current plot. So if I say y, it says current y min is 0. Let's make it minus 0.01 to 0.05 in steps of 0.005. And then I think I have to, oh no, it automatically updated. Well, that was too much. Let's go. Okay. So here is a CF plot, and again the color coding helps us realize that the yellow is upper surface, blue is lower surface. You can see the blue has got positive CF everywhere. That means it's attached flow. The upper surface has got something strange going on. It actually CF, the upper stagnation point is here, and then CF increases, and then it seems to become negative, and then it becomes positive again, and then it becomes pretty much zero and negative. So let's take this piece by piece. What do you think is happening here? That's the big turbulent separation on the back part of the airfoil, almost. So you can say, by looking at this, the separation starts at about 45% on the upper surface, and after that it's all separated. CF will be slightly negative or zero. Okay, and this, let's zoom into this if we can. So I'll go to X of 0.01 or 0.02. So I can do X from 0 to so I've zoomed in, and so this is the line that came from the stagnation point, right? It went very high CF, and then it came down. This is 0, right? So it's actually going below 0 and coming up here. What do you think is happening?
Leading edge separation bubble.
Yeah, there is a tiny separation bubble, laminar separation bubble at the leading edge. Yeah, and so that's right. Transition is 0.0076. So that's where transition is. So there's a very tiny laminar separation bubble. You almost won't even catch it if you do experiments in oil flow visualization, but it's there. And this is real. I mean, many airfoils have this. So as the flow goes around the leading edge, so it starts on the lower surface stagnation point and goes around, right? It gets its laminar flow, but then it gets this massive massive adverse pressure gradient. And we all know that adverse pressure gradient will either transition laminar boundary layer to turbulent, or it will separate it. In this case, it separates it, but very quickly the separated laminar boundary layer or separated laminar shear layer becomes turbulent shear layer, which very quickly reattaches. So it's such a tiny bubble that it's there, but almost invisible. Okay. So you asked a question, right, Ethan? What was your question?
It was basically that, but I guess it seems like it's, I don't know if it's always modeling a small laminar separation bubble to make the transition, or if it's sometimes...
Oh, right. Yeah. So, okay. Now I remember your question. So, okay. So anything on this? Any questions? There are all these other things you can plot. Delta star, theta. So this boundary layer displacement thickness, momentum thickness, edge velocity, dissipation coefficient, lots of different things. You can plot amplification ratio, which tells when the which is a measure of how the waves are amplified in laminar boundary layer to become turbulent. Let's see how that looks. I'm going to say N and see. Okay. So you can see X is still zoomed in. We are still very close to the leading edge. So this is 10%. This is 1% of the chord. And this, you remember N crit is 9. So N is a measure of the amplitude of the waves in the laminar boundary layer that are growing. So on the lower surface, well, from stagnation it comes like this and then it goes up like this, and this is where it hits 9. When it hits 9, because n crit is 9, that's where transition is assumed to occur. And that's about where transition, yeah, so that's where 0076 is actually this X location. We'll look at some other cases where this becomes clear. This is sort of an extreme case where there's a tiny laminar bubble, so it's a little confusing in some ways. Okay. Okay, so now what angle was this? 0? 0. I think it was, well, we can go here, angle, 20 degrees. Yeah, correct. So now if I run alpha 0, it's going to have a hard time, right? It doesn't converge even after 25 iterations. That's because you're making it start at 20 degrees and go to 0, and it's a terrible initial condition. So your question of how to reinitialize the boundary layer. Suppose you're in a situation where you have just done 20, now you want to go and do 0, and you don't want it to use that initial condition. So if I put question mark, one of these menu items is vpar. Where is it? VPAR, anybody see it? Yeah, there, up there. Change boundary layer parameters, right? It's a dot, so there's a menu here. VPAR, and then that means this dot down there means there's sub items, so you can say question mark, and display viscous parameters. I'm not sure what that means. It's something Xfoil is also changing, so sometimes I'm not up to date on the latest things. Let's see what it is. Show. Oh, this just says there are some parameters for boundary layer calculations, I assume, and I don't know what these things mean. So one of the things you can use, the one we are talking about now, is init. Init means boundary layer initialization flag toggle. Basically it means initialize the boundary layer and make it 0, so that if you run 20 and then you want to go to 0, you can initialize the boundary layer and then 0 will converge very quickly. See, now it says boundary layer will be initialized on next point, and then you hit enter, and now you say A0, it'll run very quickly, and that's a converged solution. So we can also say VPAR init, and then now you do A20, it might even converge. Yeah, it converged in 16 iterations. And this kind of convergence, it came with Xfoil, and actually there was a predecessor code to Xfoil called ISIS, which was written by Professor Drella. Actually, he wrote it for his PhD work, I think. Until then, this kind of convergence was really, no other aerodynamic code could handle it. And this kind of convergence happens because of this. You should go and read the paper, but he's tightly coupled the inviscid and the viscous calculations using a multidimensional Newton iteration. It's fairly complicated, but it's, really cool stuff, because look at what it's able to do. Okay, let's run a sequence of angles of attack and talk about that other question. I'm going to do VPAR init, and then I'll do a sequence 0 to 20 in steps of 2. So I think one of your questions was, what are all these little wiggles, right? So this kind of like a blip in the curve, occurs either due to transition or due to laminar separation bubble. So sometimes you may get a transition like this without a laminar separation bubble and you'll still see a little wiggle. So, but when there is a bubble also there will be a wiggle. So don't look at this wiggle and say there is a laminar separation bubble. That's not necessarily correct. So the best way to do that, okay, so that's what these wiggles are. Now to understand that better, let's go and run some moderate angle of attack. 0, 2, 4, 6. Yeah, let's run 6 degrees and let's look at this in sort of isolation. So I'm going to do VPAR init A6. So it converged really quickly and you see this little blip here. And now you can clearly see the inviscid pressure distribution and the viscous. Now, there's a little blip here and we don't know whether that is a laminar separation bubble or just like a transition without a bubble. How can we find out what that is? CF is the most reliable way to look at that. So VPLO CF will plot it and you can see transition is occurring there about 10% of the chord. That's where this occurs, right? So the upper surface CF goes to a very high positive value. That usually happens near the stagnation point. Then it falls down and it starts to become laminar, but then it becomes turbulent. Immediately after transition, usually there will be a big CF spike and then this is turbulent CF. So one thing you can see is, look at the CF here and the CF here. So turbulent boundary layer has more skin friction CF than laminar boundary layer. Now can you say whether there's a bubble or not? There's no bubble because CF is positive everywhere. So even though there is no bubble, there was a blip in the CP distribution. So sometimes CP distribution will not tell you definitively whether there's a separation bubble or not. So let's create a good, nice separation bubble and look at what that shows in these plots. What can we do to get a good separation bubble? Yeah, we can go to a low Reynolds number. I think I'll do VPAR init just to be sure, and then I'll do, oh, I went to, okay. So it's in viscous mode, and if you want to change the Reynolds number, you can use this. You can just do RE. So we're already in viscous mode. We want to change Reynolds number, and let's make it 300,000. So 0.3 million. 0.3 E6. Okay, Reynolds number not recognized. Oh, I'm not in upper menu. Somehow I went out. So Reynolds number 0.3 E6. Okay, I think it changed it. Okay, let's run alpha of 6 degrees. It converged. I'm not quite sure if I changed the Reynolds number correctly. So the good thing is you can go to this plot and it says, yeah, Reynolds number is 0.3 million. And this is where some transition is occurring, obviously, because of the blip in the curve. And you can see the boundary layer is thicker if you compare this plot with the earlier plot, which is now gone. But if you did that, you could see this thicker. Now let's go and see the CF distribution. VPLO, CF. And now you can see that there's almost a laminar separation bubble, but not quite. I don't think it went below 0. Right? So, but transition occurs at 0.3 0.36 chord, so that's about here. Now let's reduce the Reynolds number even more. RE, what did I give? 0.3 E6, right? Let's go to 100. Let's go to 60K. 60 E3, 60,000. Oh, I should do VPAR init alpha 6. Now you can see the blip is actually a big blip. And you can see something going on here. It came like it's almost like going up and coming down. That's a laminar separation bubble most likely, but really you'll know that only if you do CF distribution. And now you can see that the CF actually goes negative and then becomes positive again. So this area is a laminar separation bubble. And transition is at 0.56, so that's about here. So it becomes turbulent in the shear layer and then reattaches, and then this is attached turbulent boundary layer. Okay, questions? Yes.
Can you explain what it means when it says the Mach number is 0 and when you would want to change that?
Okay, Mach number of 0, what is Mach number?
Ratio of velocity to speed of sound.
Yeah, velocity of flight divided by velocity of speed of sound at that altitude or atmosphere. In these kind of cases, it's the velocity of the free stream, which is the velocity of flight, right? Velocity of free stream divided by speed of sound. So Mach number of 0, strictly means there is no flow speed, but that's not the correct interpretation. It means the speed of this flow is much, much less than speed of sound. So what it means is the equations being used are for incompressible flow. So that's the meaning of Mach number 0. So if you want to simulate some other condition, you should put the correct Mach number. So we can put, for example, Mach number of 0.3. And so it says sonic CP is minus 6.95 and something. Let's do alpha of 6. So Mach number 0.3 is it's almost incompressible. Okay, it's essentially incompressible. Maybe not, maybe it's getting towards that boundary where you should really put the compressibility effects. But so usually Mach number up to 0.2, even 0.3, you can get away by simulating it as incompressible flow. After that, you start having to put compressibility effects. You should consider compressibility effects. So let's put something else. Mach number of 0.6. Did it run? No, it didn't run. So alpha 6 degrees. No, you can see it took a long time to converge. That's because it's including compressibility effects. And it's actually gone sonic. So this dotted line is like the, what do you call that, critical CP? Up earlier we saw something here when we changed the Mach number. Oh, well, yeah, here. Yeah, that's the sonic CP. When we put Mach number of 0.6 minus 1.29 at Mach number of 0.6 for this airfoil is the sonic CP, and that's what is marked here, I believe. Minus 1.29, and that's what this is. So at 0.6 Mach number, this airfoil goes into not just compressibility effects, it actually experiences shock. It goes into beyond local Mach number becomes 1 and greater than 1. And when that happens, X-foil is not really valid. So even though it gives a result, this is probably really wrong because the theory doesn't account for it. So X-foil has the equations to model compressible flow, but in subcritical conditions. That means as long as the local velocity does not become, as long as the local velocity is less than 1, then it's reliable. But once it starts going to local sonic speeds, it's not, the theory doesn't work. Okay, we'll stop here for today. I think we're out of time. And then we'll continue this. I'm going to go ahead and post homework 2. We haven't completed Xfoil, but you can start looking at homework 2 and even at least get familiar with some of the documentation and that sort of thing. Okay, thanks.